So the first model we're going to talk about is a Cournot model with two firms, so just a duopoly, and symmetric costs. And so the way Cournot originally described the market was as two owners of springs of water that are each going to sell in a given period with zero production costs, negatively sloped demand, but that there will be an equilibrium price that clears the market. So each firm will sell at the same price, and that, of course, is a key component. We're going to set it up a little bit differently just to keep it in line with all of our other models. And so we will keep our same inverse demand curve, P equals A minus BQ. Now just keep in mind that capital Q will be the sum total of the output produced by firm 1 and firm 2. And then total costs are just CQ, so that marginal cost is just C. And of course, we will have one market price, right? So there will be a P star. Now, we want to think of this as a game and find the Nash equilibrium, even though, of course, Cournot didn't think of it this way. But it's still nice that it fits in to our game theory framework. So the rules of the game are as follows. We have two players, right? Firm 1 and firm 2, the owners of the firms. The strategic variable is that they choose some positive value of output, Q, and their payoffs are just the profits. And so profit for firm I is total revenue minus total cost, or just PQI minus CQI. And then, of course, in order to get everything in terms of quantities, we substitute in the inverse demand curve for P. And so after a little bit of algebra, we get that profit is equal to AQI minus BQI squared minus B times QI times QJ minus C times QI, right? And then the fourth rule is just that information is complete, meaning that I know your profit function, you know my profit function, so we know all of the information. It doesn't mean that I know how much you're going to produce and you know how much I'm going to produce. We want to find that in equilibrium. So we can solve for each firm's best response. And to do that, we're just going to take the first order conditions, like we did in Chapter 9. Remember, that's just the partial derivative for both firms. Now, the big difference between this chapter and Chapter 9 is that they aren't cooperating now, right? Chapter 9 was all about collusion. Now they're competing. And so we don't necessarily expect to get the same results that they would sort of split the monopoly profit that we saw in Chapter 9. So to take the partial derivative, so this is for firm 1, firm 2 is very similar. We get marginal revenue is minus marginal cost and set that equal to 0. And that's just A minus 2BQ1 minus BQ2 minus C equals 0. And then firm 2 is the same with subscript switched. Now, so keep in mind what this means is that the quantity that firm 2 produces is showing up in firm 1's profit function, right? And in their first order condition. And similarly, the quantity that firm 1 produces is going to affect firm 2's profit and first order conditions. Now, fortunately, we get two equations with two unknowns, just linear equations, fairly easy to solve. So from firm 1's first order condition, we have A minus 2BQ1 minus BQ2 minus C equals 0. And from firm 2's first order condition, we have A minus 2BQ2 minus BQ1 minus C equals 0. And so what we want to do is solve those for Q1 and Q2 in terms of our constants, A, B, and C. Now, there's lots of ways to do this. We could solve one of the equations for Q1 and plug it into the other equation, or Q2 and plug it into the other equation. But we can also notice that these are symmetrical, and symmetry is often our friend. And we can just say, all right, well, there's going to be some Q star that both firms are going to produce because they're symmetrical. And we can just plug that into one of the equations and solve. So if we do that, we get A minus 2BQ star minus BQ star minus C equals 0. Or A minus C equals 3BQ star. And so Q star is just A minus C divided by 3B. So we've got the quantity. Now keep in mind that's the quantity for one firm, not the quantity for the entire market. But we can use that to solve for price and profit. So we want to plug Q star back into the inverse demand curve, keeping in mind that we have to double it in order to get capital Q. And so P star equals A minus B capital Q star, or A minus B times 2 times A minus C over 3B, which gives us A plus 2C over 3. And then we can solve for profit just by plugging in Q star and P star. We get eventually A minus C squared over 9B is the profit function. So just a few things to note about this equilibrium. One is that output and profit go up with a decrease in marginal cost. So if you can increase your productivity by decreasing your costs, that's going to increase output and profit. And output and profit will increase when demand increases. So either an increase in A or a decrease in B. The price goes up with an increase in marginal cost and or an increase in demand. And the nice thing is that it's a symmetrical equilibrium, right? And so we can tell that when we looked at the first order conditions, they were just symmetry. They were mirrors of each other. And so this is called the interchangeability condition. That leads to a symmetric outcome where we can describe the Nash equilibrium of each firm by a single equation. It will usually occur when firms have the same cost functions and produce homogeneous goods and pursue the same goals. So remember, they're trying to maximize profit. They have the same technology. They're producing the same good. As we'll see in the next video, when firms have different costs, then they will have different first order conditions, and we have to solve them with just an extra step or two. Now we can also graph the Cournot equilibrium. And so what we're interested here in is the best response functions of firm 1 and firm 2 based on how much the other one produces. And so our axes here, we have Q1 along the horizontal axis and Q2 along the vertical axis. And so let's look at our best response for firm 2. Okay, so this gives us how much firm 2 wants to produce given all the possible values that firm 1 could produce. And so if firm 1 produces 0, firm 2 wants to produce A minus C over 2B. That's just the monopoly output. If firm 1 produces the competitive output, firm 2 doesn't want to produce at all because they won't earn any profits. Where they two best response functions cross, right? This is the best response function for firm 1 and for firm 2. Where they cross is where they don't want to produce more or less. They maximize their profits by each producing right there, given what the other one is doing, right? We know they can earn more if they collude because they could just produce the monopoly profit and split it. But they're not producing the monopoly profit, right? They're not producing the monopoly output. They're producing what the Cournot output is right here, and they can't do any better. And so that's a mutual best response. And remember, that's the definition of what a Nash equilibrium is. It's a mutual best response. And so that's nice. It's right between the perfect competition output and the monopoly output, which is a nice solution.